Okay, so today we're going to be introduced to log functions, and we are going to emphasize today the relationship between exponential form and logarithmic form. Okay, so logarithms are the inverses of exponential functions. That's why this book puts them one right after the other. So we did exponential functions in chapter 7, and then chapter 8 is logarithms because they are inverses. Okay, so a question I get a lot is, but what is a log? But what is it? So what a log calculates is the exponent when you are given a base and another value. What's really cool about the logs is you can write them as an exponential equation, and then you can also write an exponential equation as a log, okay, and vice versa. So we're going to go over how to write those, but you already got a little preview from that worksheet today. Okay, this is going to be one of the most important things to remember is how to write the log form as an exponential form. So you have the log base b of y equal to x. Okay, log base b of y is equal to x. And when you have that form, you can rewrite it in exponential form, which takes the same base, raises it to the power of x, and it is equal to the value of y. Okay, so we're going to be writing those different forms down. So let's look at an example. Okay, let's say you have log base 2 of 8 equal to 3. Okay, if you are writing that in exponential form, okay, if you're having trouble kind of piecing that together, one thing I use to help you remember is B, because you don't want to forget your B. B-A-B. Okay, so B stands for the base. Okay, E stands for the exponent. And then A stands for the answer. So it's equal to 8. This should also be a true statement. 2 to the third power is 8. Okay, this is what we call exponential form. And then what we have here is the logarithmic form, or log form. Okay, so if you're writing in log form, you should have a log in there. Okay, exponential, you should have an exponent. So we are going to be using those a lot. There is a special log called the common log. Okay, a common log has the base of 10. So if you see a log base 10 of some value, we'll call the value x, then you can just rewrite that as the log of x. Okay, so this is the same thing as just the log of x. So when we simplify it, when we write it in simplest form, we like to do that without the base. Okay, so this is the log with base 10. Now, some of you might recognize that there is a button on your calculator that says a log on it. Okay, the common log is the button that's on your calculator. Okay, this is the log on your calculator. Okay, so that is that log button. In our first example, we are going to write each exponential equation in log form. Okay, and then in example 2, we're going to go in reverse. We're going to take the log and we're going to write it in exponential form. Okay, so for the first one, when you are writing this, just make sure that your log base is a subscript below here. So it's log base 3 of 243 is equal to 5. And that's it. For this, you're just rewriting it in that form. Okay, so I want you to go ahead and do B. Okay, so for part B, if you wrote log base 10 of 1 equals 0, that's correct. And then because it's the common log, we're going to simplify it. So with the common log, you can just write the log of 1 is equal to 0. Okay, so if you have the common log, okay, if it's the base of 10, you don't have to include that. Okay, and it's fine if you don't even have to write that first step. If it's log base 10, you can just write it as the log of 10,000 is equal to 4, your exponent. One thing I want you to check when you're writing these is that if your 243 and your 5, see how those are on the same line? Okay, and then the 3 is below. That's how you should be writing those. Okay, so Shelly, tell me what part D, what I should write for that one. That's log base 6 of 1/6 is equal to 1. Okay, and then Akul, what'd you get for part E? Log base C. Good. Okay, so log base A of C is equal to. Okay, and again, I just want you to do a quick check and make sure that C and D are on the same line. Okay, remember when you guys were in elementary school and you guys had to do like your handwriting practice? Did you guys have sheets that look like this? Look like ropes? Okay, so when you're writing it, okay, you have the log. This A would be here of C is equal to B. Okay, and you're like, Miss Whipple, what other way would we write it? Well, every year I get something like this. Log of A, and then they have C floating up here like a cloud, like an exponent. Okay, you don't want that floating above. All right, you want it right here on that line. Okay. All right, and then for example 2, we're going to write each one in exponential form. So if you want, this is where you can use base answer exponent. So your base is 9, your exponent is 1, and that will be equal to the answer of 9. Okay, so take a few seconds to see what we have open. All right, and then Jackson, what'd you get for B? And then Royal, what'd you get for C? Great. Alex, what'd you get for D? Yeah. Great. Okay. And then Elena, what'd you get for B? Good. All right. Any questions for me on example 2? Just writing those in exponential form. Okay, now logs have special properties. These are based on the exponential form, so they're based on some things that we already know. So if you have the log base b of b, okay, that's always going to equal the same thing. Do you guys know what it is? Yep. Can you tell me why? Yes, you can. Log base b of b is 1 because, let's rewrite this in exponential form. What would exponential form be? B to the 1 equals b. Okay, so b to the first is always going to be b. Okay, and then I want you guys to try this. So an example that you would see would be log base 2 of 2. Okay, so when you see log base 2 of 2, then you can use that property. Yeah, it's always going to be equal to 1. Okay, why? Because 2 to the first equals 2. Okay, so what a log does is it takes this base and it takes this value and it computes the what? The exponent. Okay, so it's giving you the exponent for the base value and for what it's equal to. Okay, the log of 1 is also going to be a special property. So log base b of 1, do you guys know what that's always going to equal? 0. Yeah. Okay, and that's because why?
0, 1.
Yes. Anything to the power of 0 is 1. So if you have b to the power of 0, any base to the power of 0 is going to be 1. Okay, which means if you have log base 4 of 1, that's just going to be equal to 0. Okay, and it does not matter what your base is for that. Okay, so 4 to the 0 power equals 1. Okay, and then let's flip it over to the back. So we'll talk about that. Oh. With my very best $5 Anyone? I don't even think those people get a pen. Alright, so we're going to evaluate using mental math. Okay, so when you are using mental math, the way that you're going to show your work is you are going to be writing each log in exponential form. That's going to be your work. Okay, so you're going to write each log in exponential form. Okay, so that means every single one should have an equation like this. So when you're writing the first one in exponential form, you can use a variable to help you. So you can think of this as equal to x. Okay, so then you could set up 5 to what power equals 125. Okay, or I saw some of you actually plug it in because you knew as you were setting it up. 5 to what power is 125? 3. So then your answer for this is going to be 3. Okay, so this would be your work, this would be your solution. Okay, so go ahead and try that with part B. Okay, so when you see this in your book, you can just write 2 to what power is 16, okay, and 2 to what power is 16? 4, okay, so then your answer is going to be 4, okay, so what I boxed in, that's your solution. 4 is your answer, okay, 3 is your answer. This is your work. Okay, now this had a base of 2, this had a base of 5. What's the base for this one? 10, good. Okay, so this is your common log. And remember, we're not using calculators. On this swivel, it's a decimal. Does it have to be a decimal? Another way you can think of it?
No.
What? Okay, now what would that be? Yeah, 1 over 100. How do you know it's over 100, you know? Yeah, it's in the hundreds place. So if this was 0.1, I can make it 1/10. If it was 0.001, I can make it 1 over 1,000. Okay, and then you can also think of it this way. So I know it's a fraction, but if we just ignore that for a moment, 10 to what power is 100? 2. Okay, so to get the 1 over it, it has to be equal to -2. Okay, is there another way that you guys were thinking of doing Parsi? Okay, so this is 0 point, and then there's 1, 2, 3, 4 zeros, and then a 1. So 0.00001. Yes, between the 1 and the decimal. Okay, let's see if we can come up with a relationship. So this was 0.01. This is -2. Is there something we could do with the decimal that could lead us here? Yeah, you move the decimal 2 places, and then that would make what number? Do you guys know why it's 1 and not 10? No, it's something specific. It has to do with the scientific notation. Remember when you guys write it out and you have like 1 times 10 to a power? So if you have 1 times 10 to the -2, okay, you have the 1, and then you go 1, 2 from there. Okay, so that's why it is towards the 1. Okay, and I think thinking of it as scientific notation helps. So based on that, if you have 10 to a power is 0.00001, okay, we're just going to move the decimal 1, 2, 3, 4, 5 places, and then x is going to equal what? -5. Okay, and you could use this in either direction. Like if you had 10,000 instead of the 0.000, you could use that.
So when you're asking
you can write x equals or you can just write the -5. Yeah, either one would be okay. All right, let's try those 3. Okay, so Emerson, tell me what you did for part E. Good. And then what'd you get for X? Good. Okay, so to the -1, that puts the 1 over the 5. All right, and then Cody, what'd you do for F? All right, and then what'd you get? Okay, and how are you guys doing on G? Okay, so first step, 25 to a power equals 0.04. Okay, and then Addison, where'd you go from there? That's okay, tell me what you thought it was. Oh yeah, yeah, why though? Yeah, 1 over 25 is equivalent to, because how could you write this as a fraction? Yeah, well, how'd you get it? Like, did you guys start with the 4 over 100? Okay, so anytime you have a decimal, you can rewrite it in whatever place it is. So if it's 0.04, okay, so tens, hundredths, it'll go over 100. If it was 0.4, you put it in the tenths. Okay, if you had 0.004, go over 1,000. And then this one you can reduce. And you should reduce it because you're going to be able to see the pattern a lot quicker, right? So 25 to what power is 1 over 25? -1. Okay, so that is going to be your final answer. Okay. All right, now we can also graph log functions. And I already told you guys today that log functions and exponential functions are what? Not the same. They're not the same, they're what? Inverses. Okay, so if they are inverses, we talked about this in early chapter 6, like the chapter 6 we did before the exam. When you have functions that are inverses, their graphs are reflections over the line y equals x. Do you guys remember graphing that line of reflection? No, it was a while ago. And one other thing we talked about with the inverses is that the x values and y values switch. So if the x values switch, that means the domain switches with the range. Okay, so the x and y values are going to switch. The domain and range are also going to switch. Now, when we were graphing exponential functions, you always had a horizontal asymptote, which means now it's going to be what? Vertical. So remember how we always had y equals? Now it's going to be x equals. That's how you write an equation. Okay, and in many cases it will be x equals 0. Okay, in some cases it will change. Okay, and then you will need a table with 5 values for each graph, and then we're going to be using graph paper for that. Okay, so when you are graphing the function, you're also going to find the intercepts, the domain, the range, and the end behavior. Okay, so we're going to graph with our table, find the intercepts, domain, range, and behavior. So, I am going to show you how to plug this into your calculator because I want you to see some cool things that happen in the table. Okay, so when you have a log that's not the common log, there's a special way to put it in your calculator. So you can go to y equals, you can go ahead and clear everything out there. And then do anything in your calculator today. Okay, so many of the calculators, you're going to be able to use this log base. So to get there, you just have to go to math. So press this math button and then arrow up. Okay, until you get your log base. Okay, and then go ahead and press that and you'll be able to graph log base 1/4. Okay, and then some of you are not going to have this log base function. And so I'm going to show you something that we're going to learn in a later chapter. If you do have it, you can, sometimes I just put in the 0.25 instead of 1/4. And then, oh yeah, we decided, let's do the green one. So we'll put this in Y5. Okay, so you can use what's called the change of base formula. Like I said, we're all going to learn this. You can rewrite this when you're graphing. This is the same thing as the log of x divided by the log of 1/4. And I'm going to put that in here. I'm putting it in Y5 because green is my favorite color. I had a student told me that she always uses the pink one. And I was like, that's such a good idea. Okay, so log of x, and then make sure you close the parenthesis divided by the log of 1/4. And when I graph both of these together, you're going to see one line is going to go graph right over the other one. Okay, and all of the points are going to be the same. Okay, go to zoom and go to your standard because you might still have a different window. Now, one thing about this is your graph doesn't tell you the whole truth and anything but the truth. They stop here because these numbers get so small and your calculator cannot graph all the pixels. So what we have to do is we have to keep that line going. It's going to get closer and closer to 0 because that's where your asymptote is. Okay, now let's look at the table. Okay, when you look at the table, let's investigate what is happening here. So I can see these are my two graphs, they're all the exact same. Okay, you get all of these error values. Okay, you get all of these errors because you can't take the log of a negative or of 0. Okay, so we're going to write that down and not take the log. Okay, you cannot take the log of 0 or negatives. Okay, so when we start our graph, I do want you to write on there the -1 and 0, and that's going to be an error, so that when you look back, you're not like, oh, that's wrong. No, that is right. Okay, you should get an error for those values. Alright, and then let's find some other values that are going to be nice to graph. So remember how we said when you have the log of 1, it's always going to be 0. So at 1 you have 0. Okay, at 2 you have -1/2. That's going to be nice to graph. Have some decimals here. At 4 I have -1. At 8 I have -1.5. Do you guys know where the next one's going to be without looking? They're going to be 16. What do all those numbers have in common? Yep, and that's because your base is 1/4, so they're all related to that value of 1/4. Okay, so if you were to rewrite them, okay, 1/4 to the power of -2 is 16. Okay, 1/4 to the -1 is going to be 4 because it flips it. 1/4 to the 0 power is going to be 1. Okay? All right, so when we're setting up our graph, let's look at our x values. So I have to go up to 16 here. So it might be a good idea to make my x values by 2. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, and then here I have 0, -1/2, -1, -1.5. So this one might be nice to go by halves. So then you have -1 here, -2 here, oh sorry, yeah. -1/2, 1, -1.5, 2. And then we can plot our points. Which means 1, 0 is going to be halfway. 2, -1/2. 4, -1. 3, I'm at 125. 6, 2. Okay, and I find it easier to just turn my paper and graph. And we connect these with a curve. Okay, and then remember, this does not stop here. It's going to keep getting closer and closer to 0. So you just need to extend this, okay, with an arrow. So if you don't have that, please go ahead and add that on there. Okay, and then we are also going to put our asymptote on there. The asymptote can be found by looking at this value, whatever the log is of. Okay, so if you had log base 1/4 of x, your x value is 0. This is going to be the vertical asymptote. And we're just going to put that in there with a dash. So remember that your asymptote is a dashed line that shows you that it's not part of the curve here, but it is a feature of the graph. Okay, and then it says to find your intercepts. So we're going to find the x-intercept and the y-intercept. Okay, so for the x-intercept, you're looking where 0 is for the y. So 1, 0, that's your x-intercept. For the y-intercept, you're looking to see where y is 0. What happens when y is 0? An error. Okay, so because there's an error there is no y-intercept. Okay, it's 0 error is your point. So when that happens, okay, there is just no y-intercept. Okay, so again, I don't want you to think that's wrong, that's correct. No. If your asymptote is not at 0, that won't happen. Alright, and then the domain and the range. So earlier we talked about how the domain and the range are going to flip with inverses. So for exponential function, your domain was always all real numbers. So now what's going to be all real numbers? The range. So it's going to be y such that y is an element in the real numbers. And we know the domain can't be all real numbers because we're getting all these errors. Okay, and you can't take the log of 0 or negatives. You can also use your graph. All the values are getting closer and closer to 0, but they're not touching that. Okay, which means all of the values of x have to be greater than 0. Okay, so we've done the intercepts, we've done the domain and range. What is the last thing we have to do? End behavior. No. Okay, so for the end behavior, this is going to be a little different too. So we're going to do the fill in the blanks. As x goes somewhere, f of x goes somewhere. As x goes somewhere else, f of x is going to go somewhere. Okay, so before we always would look at the left and the right side, okay, because the x values would get very small. But here, the x values are never going to go past this line. It's never going to go to negative infinity. So instead, we say as x goes to 0, f of x is going to go, if the arrow is pointing up, it's going to go to infinity. Okay, so as x gets closer and closer to 0, the numbers get larger. On this side, the x values do get larger. They go to infinity. And then is this arrow going down or up? Down. So that means it goes to negative infinity. Okay, your graph, do you have to be on graph paper today? So I will put that out if you need a